right, everyone quiet down, quiet down. All right, Roberts, here we go. All right, guys. Gonna do fluid mechanics, talk about hydrostatics. Now, if you did the reading assignment, then you're gonna know a lot of this stuff, or at least it'll look familiar to you. Here we go. All right, you need to know what the states of matter are. Please be able to define what the three primary states of matter are. There's a few other special states, and they're special. Density, have some idea what density is. Density is represented by this weird looking symbol. It's not P, it's rho, Greek letter rho. Density is some mass over some per unit volume, mass over volume, and that's a thing. Fluid is anything that flows. Usually when I ask people what a fluid is, they tell me that it is a liquid, and that is true, but a fluid can also be a gas. That's a thing. You can feel it when you move around. You feel the air flowing through your hair, like me. Anyway, it's a thing. We use fluids a lot. The internal combustion engine uses fluids. So if you drive a car and it's not an electric car, then this is kind of a big deal. And then of course we've also got things like airplanes and boats, and so. But even then, weather, my gosh, fluids are very important in our lives. Pressure is force per unit area. Force is newtons, area is usually in square meters. And so pressure is usually newtons per meter squared, newtons per square meter. That is the unit, or those are the actual units for pressure. I couldn't figure out how to turn off these little noises. But anyway, we have a name for the unit of pressure. It's called a Pascal. That's the thing. There you go. These are all good things to put in your notes, by the way. So if you need to pause or rewind, that would be good. These are some of the. I've tried to pick all the big stuff and just cut out all the fat since we're online, and you know. Practice problem. There it is. Can you do it? Whew, kind of a lot of work, right? Find the volume here. Oh yeah, some of you might be asking, what the heck is a water bed? Well, they used to make beds that were filled with water, and they, I guess, felt good, and they're water beds. And so, water beds are kind of nice because they're in these square shapes, so you can easily find the volume of water. And then we use our density equation to figure out what is the mass of the water, and then from the mass of the water, we can calculate what is the weight. Fg equals mg. There's your weight, and then from there, that's your force. Force per unit area is pressure. So there you go. Hydrostatic pressure. Hydro having to do with a fluid or water. Static meaning not moving. So what we're talking about first is hydrostatic. So this is fluids that aren't flowing, that aren't moving, that are at rest. Fluids exert pressure in all directions, and they exert pressures perpendicular to the surfaces of things. So this is a thing. Look at this picture. This is a kind of a big deal, and it took me by surprise a number of years ago when I started teaching this course that the arrows on the top are smaller than on the bottom because the pressure is different on the bottom than on the top. I remember getting this wrong and being angry about it. Pressure up here is less. The further you go, the more pressure there is. You guys may know this if you've ever been in a pool and you dive to the bottom and your ears start hurting. Well, there's more pressure, right? There's more stuff above you. So yeah, are the pressures equal between here and here? No, they're not. Now, if something's floating like this, the forces can all be balanced, right? Doesn't mean the pressures are the same. So this is a thing. All right, suppose we had this this cylinder, and it's submerged, but the top of it's floating right on the, or is right at the top of the liquid, right? If we were to draw a free body, what would it look like? You'd have three forces. Where do those forces go? What is it going to look like, right? Here are your three forces. Can you draw those forces? Of course, the weight goes down. Yeah. You have a couple other forces. Actually, you have a gazillion forces, and people get upset with me. They're like, Sharky, aren't there gazillion forces all on the bottom, all on the sides, all on the top? Well, yeah. I mean, you know, fluids exert forces all directions, right? So right now there's a fluid enveloping me, and it's pushing me on all sides, right? So the idea here is that this fluid going this way and this fluid going this way are going to cancel out, right? So we don't usually draw a gazillion, arrows. Here's our picture. Yeah. You have a force that represents the atmosphere. That's the weight of all the air pushing down. Air has weight. You have a force going this way, which is the weight of the cylinder, and then the water pushes up, and all the other forces, I mean, everything else cancels out, so you have this equation that you can build. This is the thing. Okay. So this gets a little crazy. So they start with pressure is force over area. There's our equation from this last page here, right? This down plus that down has got to be equal to that up. If it's floating, right, then the forces are all balanced. Okay. And so we can insert this equation, that sucker, up in here. And then you do some math, right? The pressure up here is atmospheric, which is usually a constant at any one moment in time. Okay, so if you're doing a problem, it's a snapshot in time. That doesn't mean atmospheric pressure is the same all the time. It changes constantly. If you're going to be a pilot, you have to know that it will change, and you have to adjust the instruments in order to know what's going on outside of the plane. But problems that we do are snapshots in time, and so atmospheric pressure. It's usually this. Okay, and so what we're doing is we're building an equation for something at a depth, right? And so we have this equation, we added this equation, we're getting this thing, atmospheric is in there. We add this, and volume goes in there because this takes up a certain amount of volume. Anyway, and you get this thing right here, which is where they're going. Maybe you guys can follow all this stuff, but this is where they're going.
Anybody have an idea how to...
Yeah, I'm back. So here we go, right? So you can try to follow this. Ask me about it. This is the equation that they arrive at, and that's the big one. This is pressure at a depth. I don't call it pressure versus depth. I call it pressure at a depth, right? That's called absolute pressure. It's called initial pressure. It may or may not be atmospheric. It usually is. This is the pressure at a depth, right? Rho GH. H, they a lot of times call height. It's really depth. G, of course, and then rho. This is the density of the fluid, not the density of the thing, right? So this business is called gauge pressure. All right. All right. Here's another practice problem. You can give this a shot. Give it a shot. See if you can do it. There's an A and a B. All right. Absolute pressure. So they put in the atmospheric, and then they do rho GH, of something that is at a certain depth. Okay. Then they want to calculate total force exerted on the outside. I think this is a sub. Okay, pressure is force over area. The area, the shape of the thing is important, right? So the area, a sub they're thinking is a circular, cylindrical type thing, so it's going to be pi r squared. And so there you go. That's what they do. Okay. Closed systems, plumbing systems, things like this are very important in our lives. And so this is a relationship that you can take advantage of, that the pressure in one area of a system has got to be equal to pressure in the other area of that system. Now, the forces and the sizes of the pipes and things like this aren't the same in all those areas, just the pressures are the same. And this is called Pascal's principle. Okay. Oh, there we go. And so this is what happens here is Pascal's principle leads to something called hydraulics, which is really fascinating. And so this is how you can lift a car using a mouse. This is what I learned, is that you stick the mouse right here. You have a very small little piston. This is called a piston, and a piston is something that just moves up or down. It presses on this fluid. This is some type of fluid, hydraulic fluid, yes. And for the most part, fluids like this, liquids, hydraulic fluid, things like this, are really not compressible. They're incompressible, right? They compress a little bit, but not a lot. And so what happens is the force of your mouse gets multiplied. The force moves through the entire fluid. This area is much bigger, right? And so this equation works because the area is much bigger. So yeah, the forces and the areas can be very different. And if you have one force, if you have a small force, but it's over a pretty large area, right, then you essentially take this small force and increase the area, you get a much bigger output force. And so this is why this is how you can lift cars up, and they sit on the lift like that. Pressure in equals pressure out. So very handy equation. And this is another graphic to show that. Brakes. I talk about this in class. This is how brakes work. The master cylinder is much larger, right? And so when you hit the brake pedal of your car, that cylinder is much bigger, and it feeds to the four other cylinders, which are a lot smaller. And so this is a thing. Last but not least, buoyancy. Buoyancy is pretty fascinating. There's something called the buoyant force. The buoyant force is something that is exerted due to a fluid, right? And this is how boats float. There's this the old story about how can you take a little metal block and put it in water, it'll sink, but a giant aircraft carrier floats. And the idea is that if you can displace an amount of water equal to your or greater than your weight, you will float. So this is why boats are shaped in certain ways, right? So this is a thing. And this had to do with a guy by the name of Archimedes. I'm going to put a video in here that you can watch. It's a really cute little story about this. I don't need to tell it. You can watch it. Or you can read about it. Or you can ignore it. Whatever you're going to do. Okay. And so we actually used to do this in class where you take something, you stick it in water, and then a certain amount of water comes out, right? And if the amount of water that comes out is equal or greater to the weight of the thing, well, then it should float. This probably wouldn't float, but that's a thing. And this is how they come up with the principle. They start with F equals mg, right? Which is, y'all know that. Mass is, this is density equals mass divided by volume, and they flipped it around and solved for mass. And if you take rho and v and stick it in here, you get rho vg. This is called buoyant force. This sucker right here is called the buoyant force. This volume is the volume of the fluid displaced. You got to be real careful there. And this is the density of the fluid. Okay. Problem. Oh wow, look at all this. Okay. The trick to these problems is drawing good pictures. I think I'm going to have to come up with some pictures for y'all. I don't know, there's a picture on here. I think it's all mathematics, which kind of stinks. So, so anyway, I think I'm going to have to come up with a picture so y'all can see it. The trick is to figure out which way the forces go. What are the up forces? What are the down forces? We need to do some practice there. I'm going to have to try to come up with something, but there you go.